Howdy! In this mini lecture, we will discuss conventional alternatives to fossil fuels as an energy source. Specifically, we will discuss nuclear power. The student learning objectives of this mini lecture are discuss the reasons for seeking energy alternatives to fossil fuels, summarize the contributions to world energy supplies of conventional alternatives to fossil fuels, describe nuclear energy and how it's harnessed, and outline society's debate over nuclear power. Fossil fuels were the driving force in the Industrial Revolution and helped create the material prosperity we in the U.S. enjoy today. As you can see from the pie chart on the left, our global economy is predominantly powered by fossil fuels. Specifically, 81% of our energy comes from coal, natural gas, or oil. Examining the chart on the right, you can see that these three energy sources supply two-thirds of the world's electricity. However, if you look closely at the chart on the right, you'll also notice that nuclear power and hydroelectric power contribute nearly 30% of the world's energy source for electricity. In this mini lecture, we will examine nuclear, hydropower, and bioenergy as conventional energy alternatives that may be able to help us move away from relying so heavily on fossil fuels for energy and electricity. As with other energy sources, conventional and non-renewable energy alternatives are used to provide energy to generate electricity, heat air or water, and to fuel vehicles. They have a great potential. However, so far they have played a very minor role in most economies. Currently, we obtain about 1% of our global energy from renewables. While not renewable, nuclear energy is an alternative to fossil fuels and is the main non-renewable alternative. Notice in the pie graph labeled B, U.S. electricity generation from renewables, that nuclear energy provides 19% of U.S. electricity generation. The two of the most well-established and widely used renewables include biomass and hydropower. Other renewables include solar, wind, geothermal, and ocean energy, all of which we will discuss in another mini lecture. These energy sources are referred to as new renewable energy alternatives. Nations vary in the amount of renewable energies they utilize. In the U.S., most of our renewable energy comes from bioenergy and from hydropower. As of 2012, wind energy accounted for 15% of U.S. consumption of renewable energy. Solar energy accounted for 2.8%, geothermal accounted for 2.6%, and hydropower and bioenergy accounted for 30.4% and 48.9%, respectively. Clearly, we are relying more heavily on biomass and hydropower. Wind, solar, and geothermal combined account for just 20.8%. Altogether, renewables account for only 9.3% of U.S. energy consumption. Renewables account for 12.4% of U.S. electricity generation. While these numbers are small, it's important to note that renewables are growing faster than conventional energy sources. Wind power is growing at 50% per year, and nations are looking for ways to move away from fossil fuels while ensuring a reliable energy supply. As profitable and beneficial as these fuels have been, there are significant reasons to switch to alternative energy sources, especially if those sources are renewable. To begin, fossil fuels, as we have discussed at length, cause a substantial amount of air pollution that both cause human health problems and contribute to climate change. Switching to alternative fuels can alleviate these problems. Furthermore, many renewables are inexhaustible on society's timescale. Phasing out fossil fuels in favor for conventional alternative and new renewable alternatives will also diversify energy sources that economies around the world rely on. Renewable energy sources will also reduce price volatility, reduce dependence on foreign fuel, and create green-collar jobs due to the need for design, installation, maintenance, and management of renewable energy technologies. Clearly, there are many reasons to make the change from a fossil fuel-based economy to a renewable energy-based economy. Nuclear power has an interesting history and current standing in the modern debate over energy. On one hand, it has the significant benefit of being a clean fuel that produces no air pollution or greenhouse gases. However, nuclear power's promise of solving global climate change while still supplying us with energy is complicated by the fact that nuclear weapons are a real and significant concern. Disposal of radioactive waste is still an unsolved problem, and nuclear accidents, such as Chernobyl and Fukushima, can cause significant and long-term damage. As such, public safety concerns and the costs of addressing these concerns has constrained nuclear power's spread. Nuclear energy is the energy that holds together protons and neutrons within the nucleus of an atom. Nuclear energy is harnessed by converting it into thermal energy inside a nuclear reactor, which is a facility or system contained within a nuclear power plant that controls and sustains nuclear fission. Nuclear fission is a nuclear chain reaction where the atomic nuclei is split. See in the upper center of this slide. We use the element uranium for nuclear power because it is radioactive. Specifically, we use radioactive isotope uranium-235 for nuclear fission. Radioactive isotopes, or radioisotopes, emit subatomic particles and high-energy radiation as they decay into lighter radioactive isotopes, until they ultimately decay into stable isotopes. Some people mistakenly use the terms nuclear fission and nuclear fusion interchangeably. However, these terms do not mean the same thing, and you should understand the difference. While nuclear fission is a reality and we use this reaction to generate nuclear power, nuclear fusion is not yet a reality. Nuclear fusion is a process that drives our sun's vast output of energy and is the force behind hydrogen bombs, which are thermonuclear bombs. Nuclear fusion involves forcing together the small nuclei of lightweight elements under extremely high temperature and pressure. In the upper right-hand corner of this slide, I've provided an image of a hypothetical nuclear fusion reaction. Here you see the hydrogen isotopes deuterium and tritium being fused together. The result from this fusion is an atom of helium, the release of a free neutron, and the release of a tremendous amount of energy. While this reaction has a great amount of potential to provide us energy, scientists have not yet been able to fuse atoms together without using more energy than the reaction produces. This means there is a net loss of energy. EROI is negative, and this process is therefore not currently a viable option as a source of energy. A figure of a nuclear reactor is featured on this slide below the figures of nuclear fission and nuclear fusion. Fission occurs in the nuclear reactor core. There are fuel rods in the core that are submerged in water to keep them cool and to slow the neutrons to initiate a chain reaction in uranium-235 in the fuel rods. Control rods absorb excess neutrons to regulate the reaction. The purpose of controlling this reaction is to heat water to generate steam to turn a turbine and ultimately turn a turbine to generate electricity. One reason why nuclear energy is still a hotly debated issue is because we still do not have a solution for the waste generated by nuclear power plants. Currently, nuclear waste from power generation is being held in temporary storage at nuclear power plants across the world. Spent fuel rods are sunken in pools of cooling water to minimize radiation leakage, as seen in the top left of this slide. However, most U.S. plants do not have enough space to accommodate this type of storage, so they are now storing waste in thick casks of steel, lead, and concrete, as seen in the bottom left of this slide. In total, U.S. power plants are storing nearly 70,000 metric tons of high-level radioactive waste, which is enough to fill a football field to the depth of 21 feet. Additionally, there is also even more low-level radioactive waste. Currently, high-level nuclear waste is held at more than 120 sites spread across 39 states. The Yucca Mountains in rural Nevada were a proposed site for a centralized site for disposing of the nuclear waste in the U.S. However, political forces largely diffused this option between 2010 and 2013. One thing to consider is the advantages and disadvantages of centralized nuclear waste storage and disposal. While a remote, centralized site would greatly reduce the number of sites with nuclear waste disposal and storage-related risks, we also must account for the fact that nuclear waste would have to be transported across the country via rail and truck. Transportation of the waste could potentially put even more people at risk. Clearly, there is not a simple solution to the problem of nuclear waste disposal. The other major concern with nuclear energy is the risk of a large accident. The three main events that have been most influential in shaping public opinion about nuclear energy are 3 Mile Island, Chernobyl, and Fukushima Daiichi. 3 Mile Island was a nuclear power plant in Pennsylvania that had a meltdown in 1979. A meltdown is when an accident in the nuclear reactor causes damage to the core due to overheating. Essentially, the temperatures inside the reactor core rise to the point that the metal surrounding the uranium fuel rods melts, which causes radiation to be released. The accident at 3 Mile Island was caused by a combination of mechanical failure and human error. Citizens living near 3 Mile Island were evacuated, and thankfully most of the radiation remained trapped inside the containment building. For this reason, 3 Mile Island is considered a near miss in that the emergency could have been far worse had the meltdown proceeded through the entire stock of uranium, or if the containment building had failed in some way. Chernobyl is largely regarded as the world's most severe nuclear power plant accident. Chernobyl is in Ukraine, but at the time it was part of the Soviet Union. The Chernobyl power plant exploded in 1986, releasing radioactive debris in the atmosphere and surrounding communities. This accident was the result of both human error and unsafe reactor design. The accident killed 31 initially, but caused thousands to become sick either with cancer or other radiation-related illnesses. In total, 100,000 people were evacuated. After the accident, an area with a 19-mile radius from the plant was blocked off. This area still remains uninhabitable and is barricaded off as it is still unsafe to enter the area. The most recent nuclear accident occurred at Fukushima Daiichi nuclear power plant in eastern Japan following the 2011 Japanese earthquake and tsunami. The earthquake shut off power to the plant, and the tsunami flooded the plant's emergency power generators. Without power, the engineers in the plant could not use moderators and control rods to cool the uranium fuel. The consequence of this was that the fuel overheated and the fission process proceeded uncontrolled. While Mother Nature caused the damage that led to the meltdown at Fukushima Daiichi, many researchers have reported that the accident could have been prevented if the plant had been updated in accordance with the state-of-the-art safety standards and approaches. In this slide, you see Table 20.2 that displays the risks and impacts of coal-fired power plants compared to nuclear power plants. Read this table and consider where you stand on this issue. Specifically, would you rather live near a nuclear power plant or a coal-fired power plant? That concludes this mini lecture on Conventional Energy Alternatives Part 1. Please review the weekly outline and complete the activities for this week per the schedule set forth in the outline. Thanks and gig 'em!